Mass and energy balance for biosystem. Model 9. Energy and mass flow through ecosystem. Segment 2. Energy flow through ecosystem. It's me, Lily, from School of Life Sciences and Technology, Institute Technology, Bandung. In the previous segment, we already discussed about the introduction, and in this segment, we will more focus on energy flow through ecosystem. The biosphere and all ecosystems contained within it are open thermodynamic systems. Energy from solar, captured by Earth's biosphere, drives all biotic processes. Some of that energy is converted into biomass, drives weather patterns, thus climate. Ecosystem services are all dependent upon solar energy. The challenge for ecological engineers is to design systems that enhance utilization of this energy on the landscape. Energy enters Earth from solar as electromagnetic radiation, is transformed to heat and chemical energy, and cycles through the Earth's ecosystem. Ecosystems are thermodynamic systems. They are ultimately controlled by the laws of thermodynamics. We know that there are three laws of thermodynamics. So the first law of thermodynamics is that energy cannot be created or destroyed, but rather change from one form to another. The second law of thermodynamics is that in a closed system, energy at the end of conversion process is less than at the beginning. No process is 100% efficient. The reasons are the energy that is lost is not destroyed. It is just converted to a form that is less dense or miserable. It can be dissipated, heat, for example. And the second one, the system is closed by definition, so that is no new energy comes in. And for the third law of thermodynamics is that at absolute 0 degree Kelvin, the entropy is zero. There is no more energy to give. In energy terms, we know unit, namely Newton. Newton is the force of 1 kilogram accelerating at 1 meter per second square. And energy is the inherent force such as potential or kinetic that the system can exert. And we can represent as a joule. It's equal to 1 Newton meter. Also, we know power. Power is the rate of doing work or the amount of energy flowing through a system per unit time, and is measured as joule per second, or we can call as watts. On an average basis, Earth receives about 5.42 times 10 to the 24 joule energy from solar per year, and this energy is in balance in the Earth. About 35% of this energy is reflected back to the space from the atmosphere, and the remainder is absorbed into the atmosphere or by Earth's surface, including photosynthesis. The forms of energy and their potential for use are summarized in this table. We can know that the 35% of energy is reflected back to the space, and the remainder is absorbed into the atmosphere or by Earth's surface, including photosynthesis. The potential of this energy to do work is remarkable. The challenge for the ecological engineers is to understand and anticipate this energy system in ecosystem service design. The unit of consumption of energy for power generation is typically the metric ton oil equivalent or MTOE, and a TOE is equal to the 42 gigajoule energy. This is an incredible amount of energy. But the anticipated increase in demand for energy is staggering. We can see in the figure beside, the energy demands will increase by 45% by 2030 and an increase of demand energy per year is about 1.6%. The notion that there is enough energy in the biosphere to replace current petrochemical sources can be overly simplistic. If the elements required to create a diversified power grid are not considered, the primary source of energy that we can see in this figure are photovoltaic, wind, biomass, petroleum, coal, hydropower, and nuclear. Others may become available at some point in the future, but this is our menu for now. No energy supply is easy, cheap, or without impact. And as ecological engineers, we must be able to evaluate and assess the impacts of design on energy within a system, including human-generated energy. Energy as a unit of analysis. The concept of energy encompasses not only the energy moving through a system, but also the energy required to create the system itself. Thus, energy is the energy memory or energy embodied within a system, or energy is the amount of energy it takes to make something. And solar energy equivalent in energy are solar mJ or SCG. The solar energy of product is the solar energy required to produce that product divided by the energy contained in that product. So we can represent as the SEG per joule, or we call as transformity. For example, the emergence of spruce trees in hectare of Swedish forest is approximately 3 times 10 to the 14 SEG per annum, and the energy contained in the logs extracted from that hectare of forest is about 7.8 times 10 to the 10 joule per annum. So we can calculate the transformity of the spruce log is as the shown in this equation below. So the transformity is about 3.85 times 10 to the 3 SEG per joule. So the TR is the transformity is a measure of solar energy efficiency. In the transformities, the high value means that the system or product takes a lot of solar energy to produce a unit of energy in the system. This concept is especially important as ecological engineers to design systems to convert primary production into fungible forms of energy such as ethanol or other biofuels. For example, if the biofuels with high transformity, it will have other input requirements such as nutrients, water, and other resources associated with the inefficiency of conversion from sunlight. For the next segment, we will discuss about the tropic levels. Until then, I'm Lily from Institute Technology Bandung.